videos. It is Crystal here. Basically, I'm doing a video on Kaggle competition, playground competition, season 5, episode 9. And basically, what it is you have to predict on the number of beats per song. That's the competition. So I did the competition yesterday, I think, which was on the 2nd. And I'm happy to say that I did it on my first try, because last month I did the Kaggle competition and I did several tries until I found one that I was happy with. But on this particular one, I just used the linear regression model and it worked the first time. So I was really happy about that, because that frees me up to do other things. So what I wanted to do is I wanted to review the code for this Kaggle competition, which is the problem statement is predict on the number of beats per song. And so it's the only notebook that I have made for this particular competition. So the first thing we do after we define our problem statement, what we're going to do is we're going to import our libraries. So we're going to import NumPy as NP, which is a numeric library which performs numerical computations. It creates NumPy arrays and it also creates distributions. And then we're going to import pandas as PD, which is a data processing library which creates data frames and series. Then we're going to import SciPy, which is a scientific library, because we're going to perform a test on the train set and the test set. We're going to import sklearn, which gives you your machine learning functionality. We're going to import stats models, which is a statistical library. And we're going to import matplotlib.pyplot as PLT and sklearn, which are visualization libraries. So, and we also imported OS, which is for the operating system. So what we're going to do now is we're going to retrieve the files, and we're going to use the OS library to actually retrieve the files. And then the files are retrieved with the files that we're going to create are train.csv, test.csv, and samplesubmission.csv. Then we're going to read the files. Use pandas to read the files. So train is the train.csv file that we've converted to a data frame. Test is the test.csv file that we have converted to a data frame. And submission is the samplesubmission.csv file that we have converted to a data frame. And after we have converted the 3 files to data frames, then what we're going to do is we're going to insert a bit of pandas code to make it to where we can view all of the columns of data. So now we look at the train, and you can see the train has 11 columns of data, with the last column of data being the beats per minute, which is the target. So train info tells you that all of the columns of data are numeric. So that's good, that because all of the columns of data are numeric, then you don't have to encode any data. And all of the columns of data are floats, which is good. We look to see if we have any null values. We don't have any null values, and that's good because you won't have to impute anything. So we look at the test data frame, and the test data frame is the same format as the train format data frame, with the exception of the fact that there's no target, because that's what you're going to predict on. So we look at the test info, and you can see that on the test info, all of the columns of data are numeric, again, so you don't have to encode anything. We look for null values. We don't have any null values. So that's good. And then we check the submission file. So the submission file has one column of data for your ID and then another column of data for your beats per minute. So your beats per minute is what we're going to be projecting on. Now I'm going to perform it's a Kilmogorov.Smirnov test, which is going to test if the train data frame, the columns in the train data frame are of the same distribution as the columns of the test data frame. And so we perform the test, which is PV, underscore equals stats.ks underscore 2samp brackets train call, test call. So you want to see if the train column and the test column are from the same distribution. And then alpha is 0.05, and if the PV is less than alpha, then you're going to drop the column, because if the PV is less than alpha, then that means that there's a significant difference between the two columns of data. And then so what I said was print drop call. It said that if PV is less than alpha, then you're going to append the column to drop call. And then when we print drop call, there's like 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 columns of data are not from the same distribution. And since 9 columns of data are not from the same distribution, that's going to let you know that there's going to be problems in the machine learning aspect of it, because the columns of data are not from the same distribution. And I decided, since the 9 columns of data are not from the same distribution, that I wasn't going to do anything, that I wasn't going to drop any columns of data in that regard. But I did drop the ID. And then the reason why I dropped the ID is because in Pandas automatically indexes every row of data. And because Panda automatically indexes every row of data, you do not need an ID column. So now we're going to analyze the target. Your target is you're going to pop the beats per minute out of the train data frame. And so here is your target. And then we're going to create a histogram of the target using Matplotlib. And I've been using Matplotlib, and the reason why I've been using Matplotlib is because whenever I use sklearn, it's like invariably you get a warning. And because invariably you get a warning whenever you use sklearn, I decided to just use Matplotlib. So here's the histogram with Matplotlib, and you can see you have a very symmetrical, what looks like could be a normal distribution. So you've got your target, and then I went ahead and put the mean in there so you can see the mean. And the mean is 120. And if I had wanted to, I could have put a standard deviation in there as well, but I didn't. Or if I had thought about it really. So now what we're going to do is we're going to use sklearn to create a heat map. And then so when we create the heat map, we're going to use the color map Viridis. So you can see that the columns of data are not closely correlated. You can see that it's a very poor correlation in the columns of data. And then so I looked at core to look at the correlations, and you can see the correlations here if you want to see how the data is correlated. But the heat map gives you a pretty good idea of the correlation as well. So now we're going to define the dependent and the independent variables. So Y is your target, X is train, and X test is your test. And then we don't need to standardize the data. And the reason why you don't need to standardize the data is because it's not necessary to standardize data on linear regression. So we split our data set into training and validation sets using sklearn's train test split. And then we check the, look at the shape of the training and validation sets if you want to see that. So now we're going to define our model. Our model is sklearn's linear regression, and we just do a score. The score has a very low accuracy, but we're going to be, our measurement is going to be root mean square error anyway. Because whenever you're dealing with linear regression, what you want to do is you want to make sure that the error is as low as possible. So we predict on the validation set, and we have our validation set predictions. And now what we're going to do is we're going to evaluate the model. We're going to get our RMSE, and then we're going to get our R2. So RMSE is the mean, or the root mean squared error, really, because I put a square root in there. Because the root mean squared error is the square root of the mean squared error, and I put the root mean squared error in there. And R2 score is another, is an R squared score. So that's another type of score that you can, it's a fit test. And then so now what we do is we print the model coefficient being 0.90. We print the model intercept being 117. We print the root mean squared error being 26. And we print the R squared score being 9.4. So now we get the shape of X val, Y val, and just shows you the shape. And the reason why I put that in there is because I was trying to visualize the data, and I was having difficulty visualizing the data, so I just put the shape in there and I forgot to take it out. So now we're going to visualize the data, so you can see that we're using Matplotlib to visualize the data. And what had happened was the code that I previously had used was for a simple linear regression, which you could use, but I couldn't use it on a simple linear regression. So I went and found some code from a previous linear regression that I had done, and this is the code for a previous linear regression that I had done. And so you can see it's got a core of about 120, and it's not following the actual line. So the dashed line is your actual Y validation data, and then the dots are the predictions. So you can see that the prediction doesn't really follow the actual values very well, or in my opinion, it doesn't. But what I did was I did a QQ plot. And then whenever I did the QQ plot looked okay. It looked like the predicted line, the validation, was similar to a 45-degree angle. So the QQ plot looked okay, even though the visual didn't look very good. So now what we're going to do is we're going to predict on our test set. So pred equals model.predict x test. So you can see the predictions. And then I decided to go ahead and visualize the predictions using Matplotlib. And you can see so I did make a little bit of a mistake, because on the visualization line I said target instead of pred. But you can see that the target is a 119, or the mean is 119, and then the target is in blue. And you can see that the target is only like about from 117 to 120. So it just did give you what looks like a normal distribution, but it's not a very good range. But I went ahead and I prepared my submission. I thought, well, let's go ahead and give it a go. Let's try it out. So I prepared my submission, and the predictions are in the submission data frame of beats per minute. And then so this is what we came up with, and it was mainly 119, in that area of 119, which is why I was worried about it. And then so I saved my work and I submitted it to Kaggle. And when I submitted it to Kaggle, I got a public score of 26.39. And I thought to myself I wasn't going to do very well. I thought, oh, you're not going to do very well. But when I checked the leaderboard, the best score was 26 as well. And I think the reason why, and so my score wasn't that bad. It wasn't as bad as I thought it was going to be, because the best score was 26 and my score was 26. But I think that because the columns in the test data set are not the same as columns in the trained data set, I think that is the reason why we couldn't come up with a good score. And I just decided that since my score was 26 and the best score was 26, I decided I was just going to leave it as it is. So that concludes this video. If you like my video, please like and subscribe. And I will leave a link to the Jupyter Notebook in the description box if you want to look at my Jupyter Notebook. Thank you for watching my video. I'm afraid I have to go. I'm running late. I've got to get to work now.